This is a 1/10 ounce gold Canadian maple leaf coin, and I borrowed my boss's rolling mill to flatten this thing out to get it down to a thickness of around 6 or 7 thousandths of an inch, I believe. And I just run it through the rolling mill multiple times until the coin gets nice and flat. And what I'll do is I'll use this flat piece of gold as the cathode for the electrolytic gold refining cell. Here you can see I've got the measurement down to about 4 thousandths of an inch. And I drop it in the ultrasonic cleaner there to get all the junk off of it. And then I'll run it through the steamer there to blow any junk off of it. Make sure that thing's nice and clean before we put it in the electrolytic gold refining cell. Hello YouTube viewers, welcome back to my channel. I'm Sri Tips, and today what we're going to be doing is beginning the process of the building the electrolytic gold refining cell. What I have here is 2 bars of pure gold, and I'm going to begin this process by granulating these pure gold bars, melting, pouring it into some water. And then what we'll do is we'll get the granules out of that process and dissolve them in hot aqua regia to make some really pure chloroauric acid solution to use for our electrolytic gold refining cell. This is Hoke's book, page 253. It says, in all cases, an anode of impure metal is hung in a solution, the electrolyte, and is decomposed by the electric current. As this goes on, pure metal deposits out on a cathode. The impurities either drop down as a sludge or go into solution in the electrolyte. There is the whole story in one paragraph. But the method is simple in theory, but its successful application is not easy. Here's a sketch of the cell that we're going to use here. This is called the Wohlwill process. This is page 256 of Hoke's book. And basically what we have here is the impure anode hung in the electrolyte, a cathode made of a sheet of fine gold, and what I have here, this is what I was planning on using. This was a 1/10 ounce coin of 4/9 fine gold that I rolled into a sheet, but I don't know if that's going to be big enough. I may have to use a different cathode, but this will be my cathode for right now until I change my plans. But if you look down here, it says the impure anode runs about 98 parts per 100 of gold, or 980 per 1,000. And here's a sketch of the cell after the anode has been corroded, dissolved, passed through the electrolyte, and has plated out as pure gold crystal on our cathode. It says here that every effort is made to keep the gold content as high as possible in both the electrode and the electrolyte. As this cell operates, some of the gold in the electrolyte will plate out as pure gold crystal on the cathode. So we can't use this process with impure gold. It has to be at least 980 parts per 1,000, according to this book, in order for this to be successful. If we use low purity gold, such as karat gold, as the anode, what would happen is the electrolyte would quickly become fouled with impurities, and you'd have a bunch of junk accumulating down on the bottom of the cell here. The cell has to be stirred as it operates, and as we stir the cell, it'll whip some of this stuff up off the bottom, and it will have the possibility of getting entrained or trapped in our pure gold crystal. So we want to use high purity gold here to make this experiment work correctly. Okay, here's the procedure I'm going to use. It's in Hoke's book, page 278, Electrolytic Refining of Gold, the Wohlwill process. It says, let's see here, the cathode starting sheets of fine gold to a thickness of 0.003 inches, 3/1000ths of an inch, having an immersion area of 12 inches by 2 inches. We're going to be way under that, are suspended in rows of 4 from a silver cathode rod between the anode bars. What we're going to do is we're just going to have one anode bar and one cathode. A current of 450 amps is put through the cell, giving a voltage of 1.5 volts and an anode current density of 125 amps per square foot. Now we ain't no way gonna get that out of that little power supply that I have. We're gonna put it at 1.5 volts and see what happens. The electrolyte is a gold chloride solution containing from 80 to 100 grams per liter of gold and 10% free hydrochloric acid. We heat this and maintain a temperature of 140 degrees Fahrenheit. And let's see what else down here. Circulation of the electrolyte during operation is maintained by means of a pole airlift. I don't know what that is. I'll just put a stir bar in there and find a way to stir it as it operates. The anodes are corroded to 5% scrap in from 16 to 18 hours. The pure gold plating out on the cathode sheets in a rough, somewhat nodularized crystalline deposit which adheres firmly. I've got a big metal container here full of water. I've got my little slat of wood that's been soaking in that water set on the side of it there. So now what we're going to do, we're going to take our gold bars here, we're going to put them in our melt dish. I'm going to melt these up now and then pour the molten gold into the water. Here's our small particles of gold, pure gold, and divided up into shot there. All right, here's our pure gold. pour this water off now. We'll get this out on some heat, evaporate all the water out of here, and get a weight on our metal. Turn some heat on here. We'll dry off our gold, get a weight on it. Gold is dry now. What we're going to do, got a scale down here. I'll put my big beaker on it. We're going to tear the scale to 0. Now we're going to get the gold and pour it into the beaker and get a weight on this. Got 181.8 grams pure gold, 24K. Move our beaker off the scale now. Covered up. Well, actually, let's leave the cover off for right now. What I'm going to do is put in some hydrochloric acid. Fill it up to about the 600 milliliter level with hydrochloric acid here. I'm going to cover this beaker up now. Put it up here on the heat. Now what I've got here is concentrated nitric acid. 68% concentrated nitric acid. I'm going to put some doses of that into our beaker and begin dissolving our gold. Is 5 minutes past 10. I started dissolving the gold at 7 p.m. and I've got just about all of it to go into solution so far. That's what it looks like on the bottom there. So now what we're going to do, I've got some hydrochloric acid here, about 100 milliliters. I add that in. I've got about 50 milliliters of concentrated nitric in there so far. And so we're just going to let this continue to cook. Here you can see how much of the gold is left, pretty good right there. I'm just going to let this continue to cook until I get most of that gold to go into solution. So another 3 milliliter shot of concentrated nitric going in. Look at my silver cell. Started this up yesterday. I've got pure silver crystal in the anode filter basket there. I made a brand new anode bar for this experiment where I'm running pure silver crystal rather than the 98% cement silver. And this is after about 1.5 days growth in the cell. Into this flask. As you can see, I've got it down to about 400 milliliters. I'm just going to carefully pour it off into this jar here and save it. Rinse the rest of our solution down into our flask here. Auric acid is starting to form crystals in there, solidify on the heat. Rinse the remaining gold that's in here real well with some distilled water, and I'm pouring that rinse into this storage jar that's got my gold chloride solution in it that I'm saving, just to make sure if there's any traces of dissolved gold in these rinses, I'm going to be able to save it. Then once I get the gold rinsed off real well, I'll put the beaker on the heat and we'll dry out the metal and get a weight on it so we can determine how much gold we have in solution here and how much metal we still have left in our beaker. And that'll tell us what the concentration is of our solution. Clean beaker with the scale set to 0. We're going to take our gold that's been dried out. We're going to add it to this beaker here, and that should tell us what the concentration of our chloroauric acid solution is. You can see we only got 21.3 grams of gold that were left undissolved. That means the concentration of our solution is going to be 181.8 minus 21.3. One of the viewers has asked for a 1 gram little bead of gold. So what we'll do here is take this, measure up 1 gram of gold in this melt dish right here. Got a brand new pair of tweezers, never been used for anything. And we're going to measure up 1 gram of pure gold here. And try to fulfill that's 1.3. Let me take one out of there. Let's see. That's 1 gram right there. We'll melt that up into a little bead and offer that for sale on my eBay store. Alright, let's take this little melt dish down here. Set it down on the melt table here. Put some heat on it. It should just take a minute to melt into a little bead for us. pure gold, 1 gram. Get that for sale on my eBay store. Here's our final products. Our electrolyte for the electrolytic gold refining cell, a single 1 gram pure gold bead, and then I've got some extra pieces of pure gold left here. And if the 1 gram bead goes well, we'll make some more of those and put them up for sale. So this phase of the electrolytic gold refining cell is complete. What we've got here, this is a 1/2 liter of solution, about just a little under 500 milliliters. We started out with 181.8 grams of pure gold, and we ended up with 21.3 grams that didn't dissolve. So that left us with 160.5 grams of pure gold dissolved in this 1/2 liter of solution right here, or 5.16 troy ounces. We'll use this solution as the electrolyte for our electrolytic gold refining cell. This will conclude part 1 of that series. Thanks for watching.